Hi, welcome back, everybody. In today's class, we're going to be tackling the very interesting topic of perception. In particular, we're going to be looking at visual perception. As was mentioned in our last class, perception is really the second step in a two-part process. When we're taking in information from the environment, we first have to undergo the process of sensation, converting energies into some type of neural message that our brain can then decode. That decoding process is what perception is all about. And with all of our senses, much like it was for sensation, there's a lot to decode. We talked in our previous class about how smell sort of worked, how taste sort of worked, and this kind of first process of sensation also happens for perception for all of those different senses. But for today's class, since we're not going to be able to tackle all the different types of perception, much like our last one, we are going to be tackling just visual perception. It doesn't mean that there's not a lot to cover, but we definitely are not going to look at everything. So if you're interested in these topics of sensation and perception, I encourage you to either take a bio class or probably a sensation and perception class so you can learn more about this particular topic. To understand this idea of perception, I want you to look real quickly at this image, and just based on that quick glimpse at the image, I want you to try to remember what it was you actually saw. What were some of the characters in it? What were some of the themes? What events were unfolding? And I'm guessing most of you, even though you didn't know you only had a couple seconds to view that image, were able to, assuming you were paying attention to the slides, garner a lot of information from those just few seconds. But how did you do that? How were you able to actually process a bunch of that information that was hitting your eyes and then being sent to the back of your brains? Well, that question of how you did that, what allowed you to do it, was one of the first questions that lots of perceptual psychologists asked in the mid 1800s to late 1800s when they were trying to tackle not just how we understand everything as a whole, but how we're able to actually make sense of all the different elements of the stimuli in our environment. For vision, it was about how we're able to make sense of things like color or size or the angles of things or the structure within it. And when we got to that point, when we tried to understand this process of perception, raging debates started to form. A debate between people who used what was called the constructivist approach to perception and those who used something called the ecological approach to perception. Constructivists argued that perception was kind of a back and forth between our mind, our memories, our expectations, and those sensory organs that we talked about earlier, sending that information to our brain. In essence, it was a back and forth that allowed us to not only get the basic elements of things, but really perceive what it was we perceived. Nowadays, we tend to link this particular approach to what's called top-down processing, the impact of the mind on what it is we're actually taking in. The ecological approach argued that perception was really just a decoding process. It wasn't that our memories or expectations or anything else played much of a role in what it was we were smelling or tasting or seeing. Nowadays, we tend to link the ecological approach to something called bottom-up processing, kind of building up of our understanding of something by using all the different components that are laid out before us. This approach, well, I guess the debate between the approaches, went in a lot of different directions, but one of the first places it actually went is in a place where we can actually explore today, perception of color. In the early years, when people were trying to break down how we were able to perceive something as complex as color, we had a lot of different theories that were being presented. Once we started to recognize the basic elements of light and how it could be split and how it actually existed in these different pulses from electromagnetic sources, theorists went beyond just kind of guessing what was happening in the eyes, and they started to really try to dissect what was likely the cause of us being able to differentiate between all the different colors that we could see. And two theorists that became very popular in the early 1800s, actually mid 1800s, when we were starting to debate this idea of color vision. What were researchers named Young and Helmholtz who proposed this thing that we nowadays call the trichromatic theory of color vision. In essence, the theory was a very good link to that ecological approach or bottom-up approach that we talked about earlier. Young and Helmholtz argued that maybe when we're talking about color vision, it's no expectation that plays a role or past memories that play a role in what we're seeing, and it's instead just a byproduct of the cells being sent or sending information to our brain that allows us to see color. Now, Young and Helmholtz didn't necessarily have the tools we have today to look for those things that we talked about earlier called cones. So they had to just kind of postulate what could potentially be going on in the back of our eyes, which allowed for that message to get to our brain that allowed us to perceive color. And when they dissected how colors actually worked and how so we could decode light in a bunch of different ways, they concluded that instead of us having specialized cells that were receptive to each and every individual color, maybe we just have three different types of cells in the back of our eyes. Three that are really looking for a specific frequency of color and something that maybe is closely linked to it. They called these cells short wavelength cells, medium wavelength cells, and long wavelength cells, arguing that if we had these, it would be all we needed to be able to see the entire visible light spectrum. Short wavelength cells being the ones that were extremely receptive when the distances between the electromagnetic pulses hitting our eyes was relatively small. Medium being obviously linked to those medium wavelengths, and long wavelength cells being those ones linked to the ones where there were lots of space between the electromagnetic pulses. Of course, obviously, we're talking about relative space. Nanometers is not necessarily a really long distance, regardless of the wavelength of those cells. But nonetheless, they said there were these three different types of cells that would respond different frequencies based on how close the color we were looking at approximated what they were looking for. And we could just do some quick math in our minds to figure out what was going on with the different colors we saw. Now, for a while, Young and Helmholtz didn't have the ability to dissect the eye and look at cones, but they did have lots of other kind of peripheral evidence for this theory. One of the biggest ideas that's a kind of, I guess, biggest ideas, one of the biggest forms of proof to this trichromatic theory actually came from not people that actually used the three different types of cells, but those that struggled with color vision, those that didn't see the visible light spectrum the same way we did. Nowadays, we tend to call people who can see the entire visual light spectrum trichromats. See people that have all three types of what we now know as cones that allow us to see the colors around us. But there were a collection of individuals within the world that did have these issues that we talked about earlier, that didn't see the visual light spectrum the same way we did. A very small percentage of people were what we called monochromats, people who just saw the entire world on a grayscale, but they were extremely rare. Remember, there were three other types of color deficiencies that were recognizable. One of them was called protanopia, a second deuteranopia, and a third tritanopia. The fact that we had three different color vision issues was a big indicator that maybe there were three different types of cells that could be the source of these problems. For those who struggled with these color deficiencies, really couldn't see colors the same way others could, the lines on the top of those three different examples you see look exactly the same as the lines on the bottom, depending, of course, on the color deficiency that somebody suffers from. These aren't necessarily very common issues. Very few people in the world struggle with any of these, but the fact that there was collections of individuals within the world that struggled with these color vision characteristics, and it always happened in these three forms, was again really solid proof for the potential for this trichromatic theory. There are also other people, for those of you wondering, that suffer from what we sometimes call color insensitivities, where it's not that their cones aren't entirely missing, but they can easily be confused because of some genetic or biological impairment. There are ways to test for this. In fact, some of you might have seen these tests before, where you're asked to identify the numbers within the colors images located in front of you. For those of you wondering, if you can't see any of the listed numbers, you probably might have some type of color insensitivity, which means you maybe can't distinguish your greens from your reds or your blues from your oranges, or a whole combination of different things. 6 of the more common ones are tested for here in this image. Now, this example of color deficiencies and color problems that we talked about previously did seem to provide very concrete evidence for the trichromatic theory. And in fact, for quite some time, people concluded that Young and Helmholtz had hit it right on the nose, that color vision was really just a byproduct of us taking the information, hitting our cells, and kind of sending that information back to the brain so we could simply break it down and decode it. And then we stumbled across a big issue. One of the issues was related to how images started to look different when we transitioned from a light room to a dark room, and the hue seemed to be slightly off. Something else that was very closely linked to this was something that was later coined the after image effect. And we can actually replicate this after image effect. For it to work, what I need you to do is give your undivided attention to the screen in front of you. In particular, I want you to pay attention to the center of that X or that plus sign that you see in the flag that's pictured here. And for this after image effect to work, you cannot move your eyes, you cannot move your screen, you just have to be completely still and stare at that image for a minute straight. I'll give you some time to settle in and do that. And while we're doing that, we can talk about what theoretically is going on if the trichromatic theory is all you need. Remember, do not turn your attention away from that plus symbol. If the trichromatic theory is all we need to explain color vision, while you're staring at that plus symbol, you've got different areas of your eyes sending messages to different areas of your brain, screaming things like, I see yellow, I see yellow, I see green, I see green, I see black, I see black. And that image is just repeatedly hitting our brains without any extra information there. Because if you've been staring at that plus for a long time, you might actually have been screaming that message so long that your brain might be getting a little bit fatigued. Which when that message turns off, no big deal. Unless there's more to color vision. Unless that message is not just I see yellow or I see green or I see black, but instead could relate to I see green, not a different color. To see if this works, let's go to the next slide. Those of you that were steadfast and stared at that image long enough, I'm guessing you just experienced the after image effect. If you're kind of bummed and you missed out, don't worry. You can just rewind and stare at the image for another minute or so and have it advance to this slide. But for those of you that are experiencing this, you probably noticed that flag changed colors. You can now, probably as you're staring at the screen, see the after image effect of a red, white, and blue flag. Classic American flag that most of you have probably seen a couple thousand or million times in your life, depending upon how much exposure you've had to the flag. But how does this occur? Well, to explain this after image effect, researchers went back to the drawing board to try to figure out what could explain not only our basic perception of colors, but how this after image effect could occur, and eventually led people to something called the opponent process theory of color vision. This notion that maybe the message coming from our eyes to our brain isn't just I see green or I see red or I see blue, instead a message of contrasts. If we're seeing red, our brain is hearing I see red, not green. I see red, not green. Or if we see blue, we don't just see blue, we see blue, not yellow, blue, not yellow. So when that message is taken away and our brain has been fatigued and we have to recalibrate, well, sometimes we can misperceive colors. This also explains the dark-light contrast issue that we sometimes run into. Of course, just because we have this idea that could explain how it works, it doesn't mean we knew how it was actually taking place. As we've advanced in our science, there are actually a lot of research to support this opponent process theory. We already know that Cones seem to be responsible for that trichromatic effect that we talked about earlier. We do indeed have short wavelength cones, medium wavelength cones, and long wavelength cones. But in addition to that, we have these cells that connect to these cones and also our rods called bipolar cells that then connect to these gigantic, well, relatively gigantic cells called ganglion cells. And these ganglion cells actually accumulate information from a variety of different other cells linked to it. Then they're the ones that are responsible for the path out, the path to the optic nerve. And what we've seen is that these ganglion cells and their response rates and their patterns seemed to be responsible for this opponent process message that eventually gets to our brain. So in essence, there's a really complicated message leaving our eyes that is really just happening on the cellular level. Expectation isn't important. There's no need for past memory. In essence, we can see every bit of color through that combination of activity of our cones and the ganglion cells that are linked up to them. If you're looking to keep score, it seems to be another indicator that maybe the ecological approach is all we need for color vision. But is it really all we need? If you look back at this picture that we looked at earlier, some of you on second glimpse might have noticed some things that maybe you missed the first time. Most of you probably saw people fishing, but neglected to notice the size of the person closest to you in terms of his fishing rod and how far he has to be away from that pond to be able to fish. Many of you probably saw the boat, but neglected to note that the person sitting in that boat on the bottom happened to be shooting a gun right into a bridge. Many of you probably saw the gentleman getting his pipe lit, but didn't notice how it would be very odd for him to have his pipe lit on that hill from somebody who was in a house that seemed to be very, very tiny based on how far away it was from that hill. There are lots of other perspective issues that you can appreciate if you break this down a little bit further. We don't need to dwell on it too much, but recognize when looking at this that maybe you didn't quite get all of the things from this image. Instead, you just got the gist of it. Maybe filled in some blanks. But does this process actually happen with color as well? Do we manipulate what it is we're actually taking in to make better sense of what it is we're actually seeing? This is where we get to a really interesting effect that we call color constancy. The fact that not all colors are perceived the same way. Most researchers have just found that when we look for color and try to identify what something looks like, we use the surrounding environment to kind of better calibrate our expectations of what it is we're seeing. So for those of you looking at these images, despite what your brain is convincing you of, A and D are not actually the same color. Neither are B and C. Instead, if you remove that surrounding red and surrounding yellow environments, B and D are actually the exact same color. You can, with some fancy finger work with covering stuff up, verify that effect. How does it work? How are we able to experience this color constancy when all we're getting is information from our rods and cones and ganglion cells telling us that what we see should be what we perceive? Well, unfortunately, the ecological view can't really explain this. Instead, we had to go to the constructivist view to understand this better. And that led us to something called the Retinex theory of color vision. This recognition that our surrounding environment, our expectations of what we should be seeing, our calculation of what's around that particular light that we're looking at, all plays a role in what colors and what other things we actually perceive in our environment. There's lots of examples of this color constancy effect actually taking place. One of my favorite deals with shading and how shadows can really trick our brain. If you look at this image here, you all see a cylinder on top of a checkerboard casting a shadow onto that board. But if you were to try to discount the effects of that shadow, it'd be extremely difficult. Like if I asked you which checkerboard spot, the one on the top that's circled or the one on the bottom that's circled, is actually darker. regardless of what's actually supposed to be in that image, but just physically darker in terms of hue, I'm guessing almost everybody in this class, unless they're extremely skeptical, would guess that the one on the top is obviously much darker than the one at the bottom. But if we remove some constraints and connect those, you can actually see that they're the exact same color. The reason why we don't see it that way is because of this color constancy effect. Our brain telling us that shadows have to be taken into account and that these things can't be the same. And in fact, our brain is so dang stubborn that if we take this image away, you can clearly see that it's suddenly hard to differentiate between which one is darker again. In fact, some of you might be convinced that maybe the top one is indeed actually darker than the bottom. It's really not the case. It's just how powerful our brains can be and how stubborn they can be in these instances. When researchers started to recognize these effects in the early 1900s, different branches of psychology started to form. One of my favorite branches of psychology that started to pop up, these groups of psychologists that called themselves Gestaltists. Gestalt psychology actually bled into a lot of different areas of psychology, including clinical psychology and some of our more odd personality branches. But in terms of perceptual psych, Gestaltists had a really interesting idea when it came to all forms of perception. Their argument was that we did indeed use most of the basic elements that our eyes and ears and other sensory organs were giving us to make sense of the environment, but we went beyond that. One of the famous sayings that's linked to Gestaltist is the whole is greater than and often different from the sum of all of its parts, surmising that what you see isn't always what you perceive. A great example of this is the statement that you see on the right above. Most of you, just in glimpse, probably saw the cat, but if you look closer at that, you'll notice that phrase can't be what's there. It's either the cht or take hot, but since the H and the A are identical in the and cat portions of it, I shouldn't be able to see it in that way. But our brain automatically does things without us asking it to perceive the cat instantly. To explain how this works, Gestaltists looked for rules, tricks, laws that our brain developed as we were growing that allowed us to perceive things in kind of a simplistic way. It's not that we were doing these things incorrectly. In fact, these laws that we use allowed us to make sense of an incomplete environment. There's oftentimes things that are blocking what we're seeing, or things that can distort what it is our brain is trying to perceive. And all the Gestaltist laws and principles do is allow us to fill in the blanks, to get a more complete image, which oftentimes is more accurate than the image or the information that's getting to the brain. It's just, well, there are sometimes unexpected consequences. And the laws of proximity suggest that when you're looking at those 6 lines pointing up above the word proximity, you don't just see 6 discrete lines. You see 3 pairs of lines based on the fact that some are slightly closer to each other than others. There's laws of continuity that suggest you don't see moguls upside down and right side up and upside down and right side up, but instead you see a squiggly line working its way across a straight line. Gestaltists actually spent decades, and in fact, they're still to this day, looking for ways to explain how we make sense out of the complex, how we can take something that is, as we talked about, imperfect, and better understand it. It's not that these tools always are perfect. In fact, as I said, there's some consequences, but they do more often than not let us make sense of the world around us much, much more effectively than we could with just the ecological approach. Another interesting side effect to it is when we don't get everything, well, we can quickly, when adding extra parts, get something that suddenly looks very complete. One of my favorite examples of this is actually in the image below. Most of you, when looking at this, probably don't see anything right off the bat. And if you did catch what this image is of, probably looks like a pretty clear picture of what it is you're seeing. For those of you that haven't seen it yet, though, I encourage you to just take some time, look at this image, and eventually what this picture is of will start to emerge. And once you see it, her, I guess, everything else around it will start to become much more clear. This is Gestalt psychology at play. This is us taking what's a definitely imperfect picture and adding things to it, filling in the blanks, connecting the dots, and in doing so, creating something that's much greater than just the sum of all the different parts that are put into this picture. I'm guessing at this point about a third to half of you have now seen the image in front of you, or at least been able to identify what's in the image in front of you. If you haven't, pause, stare at it for a little while longer, and she, who is actually staring right back at you right now, will eventually appear. Once you see her, you'll appreciate why I keep calling her she and why I talked about her staring back at you. I promise, the image will eventually hit you. It's not about crossing your eyes or backing up. It's just about allowing your brain to fill in the blanks. Once they're there, you can appreciate how involved your brain needs to be to make sense of things. And just know, once you're done, you'll always see her. Next time you take a class like this or somebody pops up this image, that animal will pop up again. Hopefully that's been a long enough delay. For those of you that haven't seen it, the cow that is here is desperate for you to try to find it. So I encourage you to stare again. But for the rest of you, let's advance to the next slide and talk about where we went after Gestalt psychology. Once Gestaltists really showed the impact that our brains can have on perception, people went a bunch of different directions. One of the places they went was to take this information and use it for parlor tricks, to kind of create gimmicks that were both humorous and interesting, that really highlighted how sometimes our brain can trick us into seeing things or not seeing things that maybe we didn't want to see or maybe did want to see. One of the classic examples of this is the young and old woman that you see pictured in the upper left-hand corner. Some of you, when looking at the image, probably instantly saw an old woman looking down, while others saw a young woman looking away. And unfortunately, regardless of which one you saw first, the other one probably is significantly more difficult to see now because of that first perception. But if you look closely, if you really try hard, your mind will eventually allow you to see the second one. But I want you to identify how difficult it is to change your perspective once you see it. Another thing related to Gestaltists research and kind of our focus on things like floor and ground and perception can be seen in some of the other images that are pictured here. The basic cube that you see in your upper right-hand corner might look fairly benign. I'm guessing some of you see it going down toward you, others maybe see it going up toward you. Now what's really cool is if you stare long enough and change your perspective just a little bit, you'll be able to see it shift from down to up or up to down and back. This is based on what you're focusing on and how your eyes are bending at very specific points. And research on this can highlight again a better understanding of how perception at the cognitive level works. It can also explain why most of us, when we look at the vase in the lower left-hand corner, don't notice anything really that interesting about it, despite, I guess, it being kind of misconfigured. But if you look at the shadow that that vase casts on the wall, you might very quickly notice something that you missed on first blush. Looking just at the ground and the background, you might quickly see the faces that are actually in that vase, or to be more specific, the two profiles that are in that vase. How we can shift attention away from things, how we can create these visual illusions was something that psychologists really did get interested in. long before psychology was around, but really tried to solve when psychology started to take shape in the 1900s. But also was something that we kind of found interesting was how throwing three-dimensional images into a two-dimensional space could really mess with people's minds. Classic example of that is the picture in the lower right-hand corner. You might have also, in your days looking at different images, seen the elephant with either 4 or 3 legs, depending upon which perception you take on the matter. All of these things really highlight how important our brain is in the perception of information. And this led to, again, not only researchers trying to understand all these different components that we use at any given moment to perceive things, but how we could maybe benefit from some of the oddities that happen in perception when people are put in very untraditional situations. And these oddities are things that led to a whole slew of very famous optical illusions that you might have encountered along the way. One of my favorite optical illusions was something called the Mueller-Lyer illusion. It's one that uses our, again, expectations of three-dimensional spaces on these two-dimensional images to trick our minds into misjudging size. If you look at the lines on the left and the right, you can see, for one, the lines are kind of extending down from a center line. On the other one, the lines are extending up and out from a center line. If I were to ask you which line, middle center line, was longer, the one on the left or the one on the right, you might, if you've never seen this, think I had to be joking. Most of you are probably convinced that the one on the left is significantly shorter than the one on the right. But if you take away those arrows, the one's pointing away and the one's pointing in, what you'll find is kind of interesting. These lines are actually the exact same length. And this is the basic Mueller-Lyer illusion, but others have been devised over the years to really highlight how this works. And many have tried to explain how this works by looking again at the brain and how we're able to break down what information is actually getting to it. Another very closely related illusion that's been celebrated by many is something called the Ponzo illusion, one that looks at how our brain, kind of unintentionally sometimes, uses this idea of something called vanishing points, especially when looking at three-dimensional images on a two-dimensional picture, to kind of judge size and length. The classic Ponzo illusion is pictured on the left when people are asked which of the horizontal lines, the top one or the bottom one, is longer. Most of us see the top one is slightly longer than the bottom one, but I, in all honesty, at this point struggle to really see them as different sizes. And if you want to see a new, more updated version of the Ponzo illusion, just look to your right. If I asked you which of the shaded lines was longer, the one on the left or the one on the right, I'm guessing everybody in this class right now is convinced that this must be an error. The one on the left, even though you know I'm going to tell you is the same size as the one on the right, can't be the exact same size. And I promise if you take a ruler to these things, you will indeed find that those are the exact same length. Another example, the Ponzo illusion, and how when vanishing points start to get into play, our brain can truly be tricked to see things in ways that, well, just aren't true. I do need to remind you that doesn't mean that our brain is creating lots of errors. More often than not, almost every single time, in fact, our tricks that we use to be tricked here are useful. That they help us perceive size more accurately and perceive distance more accurately. But in rare cases, when we can access these illusions, we can get more information on how the brain is doing what it does. If you're looking for really the, I guess I wouldn't call it the culmination of years of work, but kind of the highlight of how much we can trick the brain, you don't have to look much further than the Bay Area. In fact, in a very popular place called the Exploratorium, they've devised a room that's been replicated in many different places. In fact, I think the Exploratorium replicated this room from other places, called the Ames Room. It conspires to get us to see images, but what we're seeing in a very different way. the perception of size can get thrown off dramatically based on the surrounding environment and some of the tricks that Gestaltists and other perceptual psychologists discovered over the years that we're using to perceive size and distance. If you want to understand how this Ames room works, what's great about it, I encourage you to not only look at the linked video that I put on the website, but also go online and search out the Ames room, or for that matter, go to the Exploratorium and check out the Ames room. I'm guessing what you'll find is something that really does boggle the mind and make you really appreciate how involved your brain is in this perceptual process. So we want to go back to one last thing here before we close out class. I'd love to revisit that debate that we talked about earlier, the constructivist versus ecological debate in psychology. When we talk about perception, most people now conclude that our brain is constantly playing a role in a lot of the different things that we're perceiving. And it's not just decoding what's there, it's adding, it's embellishing, it's altering. But it's really important to note that when we talk about the importance of this constructivist view, that we don't overlook the critical nature of the ecological view as well. Not only is top-down processing really critical in our perception of almost everything we see and hear and taste in our environment, but so is bottom-up processing. It's really the merger of these two processes that allow us to see, and hear, and taste, and smell, and all the other senses we have the world around us. And this is what I want you to take from this video. We've gone a long way. We've covered a lot of different things, and we've definitely veered in a lot of different directions. But if you can appreciate how complex just something as simple as sensation and perception can be, you can understand the really tough world that psychologists have tried to tackle for a century plus, and will probably continue to tackle for a century plus. When you've got that down, it's probably time to start moving on to the next module. In the next module, we're going to be looking at another early branch of psychology that started to try to understand the human mind when they looked at it on kind of the surface level. In particular, what we're going to be doing is looking at a branch of psychology called behaviorism. Until then, I wish you all the best. Make sure you get those posts done as soon as possible. I'll see you soon. Take care.